Mean free path. This is the idea that the particles travel in a straight line until they run into something. And that distance that they travel is their free path. And mean is a word that means average. So this mean free path is the average distance that a molecule travels between collisions. If nitrogen molecules were the size of a golf ball, those nitrogen molecules would travel about 40 feet in a gas before they actually run into anything. That's quite a long ways. So here we can picture this red molecule, and it's going to travel varying distances before colliding, but it will have an average. We know that gases spread out. They expand to fill the volume. I have 5 boys, and so there's a lot of farting that happens at my house, and accusations of whose smell that was. We all know from experience that someone can let off a little toot in the corner of a room, and within a few minutes, that smell is everywhere, right? You didn't do anything to stir it up or move it around. It just spreads, and that's the nature of gases. That's called diffusion, where gas molecules spread out from a high concentration to a low concentration. Heavier particles move more slowly, and so they diffuse more slowly. Smaller particles move more quickly. They will spread or diffuse more quickly. So that's diffusion. Another word we need to be familiar with is effusion. And this is the process in which a gas escapes through a small hole into a vacuum. So gas is going through pinholes, basically. And the rates of both of these are related to the average velocities, the root mean square average velocities. So if we have gases that are at the same temperature, then the rate of gas movement is inversely proportional to the square root of the molar masses. So that's this guy right here. That's called Graham's law of effusion. So if you remember, that root mean square velocity, 3RT over the molar mass. So if we take the ratio of the velocities, we get this. So the rate of A over the rate of B equals the rate of B over the rate of A. They're inverse. High velocity, small molar mass, and there's a square root involved. This is what effusion might look like. Here you have a vacuum on this side and you have helium on this side. The gas is going to travel in a straight line until it runs into things and it's going to bounce. It's going to stay in this side of the container, even though there's a hole here, until it happens to have that hole in its free path and it goes straight through. It makes sense that the faster these particles are moving, the faster they'll get through the hole, right? Okay, find the ratio of effusion rates of hydrogen gas and krypton gas. Students hate problems like this. There's no numbers. What do we do? I know it makes it hard. So, ratio of effusion rates of hydrogen and krypton. It's not specifying. I'm just going to go with hydrogen on top and krypton on the bottom. So the rate of hydrogen to the rate of krypton. That equals the square root of the ratio of their molar masses. But this is upside down. I don't have hydrogen on top here. I've got hydrogen on the bottom and krypton on the top. So the molar mass of krypton is 83.80. Do the units matter here? No, because they're going to cancel out. I could do grams per mole, And the fact that I didn't convert to kilograms is not going to matter. You can convert to kilograms and you'll still get a correct answer. Hydrogen is diatomic. Needs a decimal point. So we've got the square root of 83.8 divided by 2.016 equals 6.447. There's no unit there. That number doesn't look like a ratio, does it? We could say that's 6.447 to 1. So hydrogen is going to effuse almost 6.5 times faster than krypton. Have you ever noticed if you have a balloon that's full of air and a balloon that's full of helium, the helium one will shrink faster than the one with air? You could try that at home. The reason is that helium atoms are smaller than the nitrogen and oxygen molecules in air. They move at faster speeds, and so they hit the little tiny pores in the latex balloon more frequently, and they escape.